See a red light? I think I'm recording. Hi boys and girls, it's me Butch. My name is Terry David Silvercloud. Am I recording? I think so. And I'm 74 years old. Today is the 24th of November, Saturday, 2018 in Vancouver. It's a cool, rainy day. And it's 20 after 1 p.m. So I live alone. I'm not shy but quite reclusive, and in my old age I keep busy working on my art and making videos just to distract me from my arthritis and make having gotten up in the morning worth having gotten up. So today I'm going to attempt to talk about the concept of folding space. And before I do that, I told myself to remind myself that I should clarify a few things. There's a lot of fallacy of ambiguity in the world, and particularly in the world of science and physics. I'm doing my very, very best to follow every single law of physics and science of which I know, that's for sure. And but you need to know everything I'm telling you is my opinion, my theory. I strongly encourage you to research everything. A good scientist or a good detective leaves no clue, no matter how idiotic, uninvestigated, because you just don't know what you don't know. So where were I? Fallacies of ambiguity. I was going down this. I got off on one of my trips there. Oh yeah, unified particle theory. Unified particle theory is subject to fallacy of ambiguity because it really covers two seemingly different area of physics. One of which describes how a group of particles, which should in theory all be identical but need not be, but assume they're all the same, like the shots in a shotgun. When a shotgun goes off, the pellets, they're all the same size little balls, but they're unified as they travel through the air. So that's a swarm of bees, of birds or locusts or things all moving seemingly as a unit, a swarm of drones even. Those are unified particles, but the other meaning is in the world of atomic physics, finding some basic construct which unifies the construction of all material. So happily, the two need each other anyway, and the stuff of which I'm talking about covers both concepts. And today it has a little bit more to do with unifying all the different kinds of particles out of one basic somethingness. And I don't want to drift on too long because I'm a regular motor mouth and ADHD and you name it, and I'm also comfortably numb. I think I have enough tokes today to numb my arthritis and ready to go. So where am I going to begin? Now the basic problem with the universe is I'm sitting at the center of my universe and you are always at the center of the universe, just like you are always standing directly above the center of the earth. Everything is connected to everything else, but in an infinite reality that just goes every direction forever and ever and ever and ever and never stops. That's hard to conceive, of which to conceive, but we're going to sort of try. If you had a universe made of a single material and the entire universe from coast to coast, infinity to infinity, was solid, that poses a host of problems. It'd be very hard to get around. But it immediately implies that if something is solid, it must be made of smaller bits and pieces, or it should be able to be made of smaller bits and pieces. And mathematically, you run into a problem immediately. And the Greeks kind of thought they had it nailed down to a regular tetrahedron, but the mathematicians tell me, and I'm not fond of math, I'm a lazy kind of person, and math is pretty tedious without the help of computers. I'm more a visionary person, that's why I enjoy painting and stuff and photography. The Greeks thought you could tile the universe, which means if you had a solid universe and every brick was the same size and shape, that you could do it with a regular, that's a perfect tetrahedron. And a tetrahedron is any shape that has the minimum number of vertices, the pointy parts, the minimum number of edges, the liney things here, and the minimum number of faces. And mathematically, you can only do it with this shape, but this shape comes in all sizes and shapes, or there's all kinds of ways you could squish it. But if you thought of it as a volume, then you would really want to get back to the tetrahedron as being the best way, the regular tetrahedron, a perfect one. This is a right angle tetrahedron. Right angle tetrahedra are exceptionally strong. They like, they make really great tripods. So right angle tetrahedra are very strong. But when you still have a solid universe, you run into the problem of trying to reduce the universe to a single building block of a particular shape. And you can't do it with tetrahedrons, and that's the universe's problem. It would have to crack. There would always be a bit of space left over. So let's fill the universe with water. Now we got ourselves a fluid, and fluids like water can have all kinds of things dissolved in it, and they're all happily associating with each other, just peachy keen. And if we had a gas, it would be similar, but the things that were really solidy would now have to find some way of fighting it out amongst themselves. And that's sort of what we've got, but a combination of solids, liquids, and gases. And you just have to look out in space. You don't take my word for it. Solid stuff, air stuff, and I'm going to drink some liquidy stuff here. Eggnog. Dairyland, too sweet. I like the Lucerne better. But it was on sale. Where were I? So let's go in the medium here for purposes of description. And the very first thing you got to get out of all this is that regular tetrahedron, tetrahedra, can't tile the universe. You can get into a pretty neat kind of tiling of the universe by using right angle tetrahedra. Here's a big one. So these shapes can form a net around a cube, or they could be the basis of an octahedron. And well, there's where those glasses went. Just found the glasses. I didn't step on them. So one of the really basic shapes in the universe is an octahedron, and you'd recognize each side as being an Egyptian sort of style pyramid. So this is an octahedron, and I know I've missed something here that I meant to talk about, but that's okay. I'll get around to it. What I want you to look at first before I remember whatever it was I was supposed to do, so I want to see if you can see in there. Can you see in there that At the base of a pyramid on the ground, it's a square. So at the base of every pyramid, there's a square, and if you were to take the square and make an X from corner to corner, and you called that unit number 1, it's the very smallest unit there is, unless you divide it some other way, which you could, but we're not going to worry about it. Now, if you get back to the idea that it's a square, I want you to think a little bit about our friend Mr. Einstein and his E equals mc squared. Okay? So E in physics is the electron. I'm monkeying with this formula a bit, and the really serious physicists will know that I'm using this for demonstration purposes only. Okay? So this is our smallest unit of energy as well, but energy is denoted by a big E. So little e here, it's not, it is energy, but it's for an electron, which is the unit we use to measure other things. It's our ruler. We can't see anything smaller without using electrons. Our brains work on electrons. Our eyes see with electrons. We live in a universe that is ruled by what we think is the smallest baryon. Baryons are protons, neutrons, and electrons. I'm going to tell you because I'm going to yak forever here if I don't keep going. In my world, electrons have the shape of an icosahedron, which is a 20-sided spheroid, but not a sphere. And the reason for that is if you're looking for the smallest of the small, spheres won't do. This can't be an electron, because if it's a sphere, it means it has zillions of smaller parts, and that's just not a very practical idea, because an electron is already getting pretty close to zero. But if it's the shape of an icosahedron, and this is my opinion, then it can switch poles easily, and it can spin easily, and it's an extremely stable shape. Where am I? We're going to be talking about folding space eventually. I'm getting there. So remember, I had the square at the base of the square here at the bottom of the pyramid. If the base is our basic unit of next to near nothingness, and you look at the formula E equals mc squared, you see that it, even though it's really a vector kind of a mathematics, which is giving you the energy of a force. We measure mass by an amount of energy, the ability to do work. So mass is measured in, like I'm about 200 pounds. That's my mass. But that just means that's the force I'm exerting against the earth as I'm being pushed against the floor here. And the electron has mass. It has here-ness and there-ness. So when old Einstein gave us this sort of basic concept, E equals mc squared, he was really giving us something which would be easy to work out vector lines of force, but it wasn't really dealing with volume. And the reason for that is that he did all his first stuff, relativity stuff, back in 1916, and the idea of waves was all brand new. Electricity was all brand new. I mean, he was living in a gaslight era, basically. And electricity was all new, and radio was new. And eventually quantum physics would come along in the 1930s, and it would find a way to talk about spheres of energy, and those spheres are called photons. So the fundamental photon that's used in quantum physics is the one that belongs to the electron. The very smallest photon is the electron. If there are smaller ones, it doesn't matter. They will still be measured in terms of that particular photon. So the electron, mathematically, in terms of energy, is a sphere, and it's a photon. And what you need to know is there are as many photons as there are frequencies. But the smallest one is that of the electron. That gives rise to some strange things you got to think about, that if an electron relatively were sitting still and it rotated only once a second, it through space would have had to have traveled nearly 300,000 kilometers, because that would be the speed of light. So it means we are measuring the speed of light against whatever the electron is, but it's really teensy. So relatively, it didn't really have to go that far to be going at the speed of light. It didn't have to go 300,000 kilometers, because a second is when you're this tiny, that's like forever. I mean, if you give me a few years, I can walk around the world, and the electron could get from here to there if you gave it enough time. But in its world, it is so teensy that it doesn't really have to go that far to rotate once in physical actual distance. It just doesn't have to go through space that far. All it's got to do is start rotating. It gives rise to the fact that the frequency of 1, if it's set by an electron, it means that you can start measuring, well, how much force does it take to either spin an electron or get it to actually move? And I started thinking of two things here. How much energy we need to do that? Well, we need whatever the mass that's filling the electron, we need another one equally as big as this to say, move over. We can measure that, but we can't do it well with the E equals mc squared. We can do it with photons by saying a photon is one quantum. And now we need to find a way of, like, where does the one quantum and the E equal mc squared get their act together? Well, it's sort of the square, and the sphere is inside the square, or either way around. It doesn't really matter that much. But let's think about spinning it here. So if we wanted this to spin 100,000 times, say a second, we would need a lot of energy, and the energy is determined by this formula. Energy is equal to the Planck constant times the frequency, or if you prefer, the Planck constant times the wavelength. The frequency and wavelength are intertwined. If you have a wave, a complete wave is where you go up, down to the other side, and back to where you started. So all waves have a push and pull, or an up and down component. If it isn't up and down, it's push and pull, or that's the only easy way I can describe it to you. But if you make the poor old electron start spinning too fast, there's going to be a point where the energy it reaches in its own spinning the same amount of energy of a similar volume that would try and push it out of the way. And we can use the E equals mc squared formula to determine what that is, and it would be the formula for the volume of a sphere where the radius was the speed of light for any amount of time, which is this. It doesn't say how, just the speed of light for how long. Well, here we use it against a second. So, but it would be the same, exactly the same idea. And the formula, did I say it yet, is 4/3 pi c cubed. Or the formula for the volume of a sphere is 4/3 pi r cubed. So we just substitute the radius for any given amount of time, in this case a second, with the speed of light, and we come up with 4/3 pi c cubed. So that would be when the energy of a photon, that would be the same as a quantum, and somebody's got to move, and the moment one of them has even a pinch more than the other, somebody has to move. This is obeying the first law of thermodynamics. So generally speaking, if I haven't yacked about that already, I'm going to generalize it this way. The first law of thermodynamics basically says you can't get something from nothing, and you cannot create nor destroy energy. If something gains energy, something else must lose it equally at the same time. So if something gains spin, if this electron was gaining spin, the rest of the universe somewhere had to contribute that energy to that spin, which would further contribute to the contraction of the rest of the universe, where it had to somehow react. And for an electron, when the energy that's going into it, the spin, finally exceeds what it can spin, it quite literally, physically jumps out of wherever it was contained and to the next level where it's comfortable, and that's called a quantum leap. That's what it takes, one quantum or one photon of energy to do it. So that's how the original photon got into the electron, and it takes another electron to make an electron move. But I want you to think about that 4/3 pi c cubed thing in your mind. Where was I? Because I want to move on here. I tried to get across to the idea there are photons. The teeniest one belongs to the electron, but every wavelength after that, for every time you make the electron spin one more time, you create more and more photons of the electron size, and as they gang up, they just become bigger and bigger photons. So the photons are a measure of energy in a spherical wave form. So if you have a frequency of 25, it has its own photon. And if you have a frequency of 2000, it has a much smaller photon, but it was space being compressed. Another way you can look at that is that a red photon, which is about 0.666 microns in wavelength, compared to an electron, is much, 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 much bigger than the photon for an electron. But if you could compress all of that energy down by making this thing spin faster and faster, so it gained energy, it would start shrinking, because now it doesn't need as much space because it's spinning faster. It would shrink down to this size. So the red photon and the electron, the red has I'm somehow going the wrong way here, and I don't want to do that. This can be very confusing. You see, it's even turning my mind to rubber. It turns everybody's mind to rubber. The important thing here, because I'm going to confuse myself as well, is that the photons are a measure of strength, but not of energy. They're big. They're big and bullies, but they, a smaller photon would fill the big one. If you get it, that's sort of what I was trying to get at, I think. A red photon is really a lot of tiny little photons. And when you get enough to make the wavelength of the red somewhere around 680 to 690 nanometers, that red photon is big enough, the light photon is big enough to, if there was an electron happily encamped on certain types of material and a red photon hit it, it would literally jump out, and we get electromagnetic or photoelectric effect from that, with things like light meters and solar cells. That's what's doing it, is these longer and longer wavelengths. And it turns out that matter really starts having issues when wavelengths get longer than 1 micron. That's no surprise, because the wavelength of heat happens to be just a little bit less than around 1 micron. So anything of that size physically is also the same physical size as the photon for heat. And when they start colliding, they're going to start resonating and heating up. But what happens... Have I lost you? I think I lost myself there for a minute. I'm on to this. We'll get to it. You need to know that energy is dependent upon either frequency or wavelength times a value called the Planck constant h. And to make something spin faster, you have to keep adding another one of these Planck constants to it. So the faster something spins, the more the more Planck constants it took to make it do that. I don't know if you got that or not. Doesn't matter. We covered that I try and get the relationship between E equals mc squared and volume, and that volume is photons. It's not solids. It's a mathematical way of quantifying energy in relation to frequency or wavelength, which are the same thing. Each frequency has its own wavelength, and each frequency has its own size of photon for mathematical purposes. But in quantum physics, we're only really interested in the photon for the electron, which is 1 quantum. So waves, when they get going, when things start, this is what happened when this thing was spinning so fast that the energy in the spin was equal to its original energy. Something's got to give. And it can jump out of its orbit, and that's what it does. So on a wave, if you're watching water waves, what happens is the tops start to roll over. This is where the E equals mc squared starts going into the E equals 4/3 pi c cubed. The waves start forming, and what's really happening underneath here is there's a ball of energy under each wave, and the ball, instead of rolling evenly, is slowing down in its forward motion and breaking. I'm trying to get across the idea that waves, when they reach a certain forward push, have no choice but to start breaking on the top. And that's sort of what is happening in space here. It's the same idea. Space has compressed and started to spin to take on energy, and energy can neither be created nor destroyed. So a shape of energy is formed by spinning, and the spinning slows down time. What? Well, here's the thing. If you were here going forward, but you could spin back around backwards while you're moving forward, you would be trying to cheat going forward. You are folding space. Spinning is a way of preserving energy into more and more spherical or spheroidal shapes and slowing down time. I'm losing myself here. Jeez, I really did this time. I think I've sort of got you into the idea of how a fluid universe gets distorted so easily and why. You know, if energy can be changed by spin, anything which can fold itself closer and closer to a spheroidal shape, which will be the very primal shapes of reality, if it can start spinning just like, if it can start spinning so fast that this point here can go around and come back as fast as anything can go from here to there, it is now being here, there, and there, sort of at the same time. It has achieved E equals mc squared. What we want to try and do is make it achieve an even faster spin than it would take to get from here to there and back again. At the same time, it would take the ordinary smaller thing to cross that flat plane and get over here. Are you getting that yet? Let's try that again. It just has to be able to spin a rotation fast enough that this point here can go all the way around and get back here before the same point traveling at the speed of light could get from here to there. So if a thing that was here was traveling at the speed of light and trying to get to there, but this thing spun fast enough that its start point went all the way around and got back there at the same time the one that started from there, it has achieved E equals mc squared. It has folded space. But it's kind of a useless space, isn't it? It's this kind of flying, disky kind of thing. But the moment it started spinning, it caused the rest of the universe to react. Energy ain't free. It had to obey the first law of thermodynamics. If it gained energy, the rest of the universe had to lose energy, and it means the rest of the universe had to shrink. It had to start finding a way to become solid. You must freeze. It cannot be helped. You must obey. I'm God today. You must obey the first law of thermodynamics. And it says, okay, but wait, may we remind your Honor of the second law of thermodynamics. And God says, oh, what's that? He says, and the second law of thermodynamics says that all things made must fall apart. Oops. Well, darn. So this sets up an eternal conflict in infinity. The first and second law of thermodynamics and the fact that you cannot tile the universe with something perfect, the fight goes on forever, and solids are not possible. And gases are not possible. Fluids, maybe. But what would be neat would be gas with particles. So that's sort of, if you look at it there, it's sort of the way it is, but it's also how you see size. If you were down here and this was an electron, a second would be a really long time, and a mile would be like, what? I ain't going no mile. You expect me to go 300,000 kilometers? You expect me, my little electron, to go 300,000 kilometers in 1 second? You're out of it. But if the speed of light was how fast the messenger can actually travel, then it's really only how fast the electron can get from here to there, or how fast it can rotate once. So the electron in our size universe, because we are built of electrons and we are built of things that are constructed from electrons, electrons rule in our size universe. At the smallest of the small, the universe cannot get its act together, and over infinity it's struggling and it's going on right now and everything's whirling around. But at the very smallest of the small, there are shapes. And it turns out that right angle tetrahedra are a pretty good shape, that they can be used to construct octahedra, and certain right angle tetrahedra or irregular type tetrahedra can be used to make things like Johnson solid J13, which I'm going to tell you, this is my opinion, 5 gamma particles make an X-ray particle. 10 gamma particles make a neutrino. A neutrino plus an X-ray particle makes a tau neutrino. A neutrino plus an octahedral, or if you take if you take a neutrino and 2 X-ray particles, you have yourself an octahedron, which is an electron. If an electron on one of its many pentagonal sides takes on a neutrino, which doesn't have a very long life, but it might get parked there momentarily, it is an electron neutrino. If an electron has 2 of these neutrinos parked on either side, it also is not very stable, but it would be a muon. I'm telling you this because of the folded space idea that starts with the idea that at the smallest of the small, where'd my door go? Jeez. What happened to it? Well, isn't that neat? There it is. At the smallest of the small of the small of the small, I can't quite see my screen, is E equals mc squared. And for us, in the dark matter world, it is what it is in the dark matter world. We are so big that dark matter is grease. And it's so tiny by our large structure. We are following the laws, I am telling you this, of flotation and buoyancy in a universe which acts like a fluid or a gas, take your pick, it doesn't really matter that much, where there is no up or down, and up or down is determined by spin, and the more spin you have, the more energy you have, and the smaller you are, the more likely you are to start becoming what seems like a solid. And bits of solid, just like the dust bunnies in the corner of your room, start making bigger and bigger solids based mathematically on the idea that if you start with a right angle triangle where the equilateral triangle has sides that are the root of 2, you will start exponentially multiplying that, where it goes square root of 2, square root of 4, square root of 8, square root of 16. Excuse me. It all started with folding space with right angle tetrahedra. They just build up from nothingness. It's not hard to imagine how just little. If you start, the most basic shape has to be a triangle. And that's the most basic shape there can be of a flat surface. And if you gain a surface, that is an area of rest, and crap will start accumulating at the center, and it'll work its way out to the edge. and it will just form a natural right angle tetrahedron. And why a right angle and not a regular one? Well, a right angle tetrahedron is the most stable. It's obeying the second law of thermodynamics as best it can. If it was a tall one, it would have to decay down to a right angle one anyway. And if it could get together with another one on the other side, then it could form itself a shape which would be a dual of itself, and that would be extremely stable too. So in my mind, I'm still working out whether the dual is a gamma or whether the half is a gamma particle, but it's easier in my world for the way I'm working it out that a gamma is a right angle tetrahedron, but it could also be have the same volume and take the shape. Space is not quite solid until the electron, and we view everything with electrons. I think I've talked way too long. How long have I yacked now? See, I got on for 41 minutes, and I don't even know if I made my point. That's the way I am. What should I have covered here? Fluid dynamics. That's how space is working. You know, the spheres are very large-scale things, really. I mean, I know this is small, but when things get really, really big, you're trying to deal with more and more volume, and spherical is also relative to your size. Like when my floor looks perfectly flat, or the Earth looks perfectly flat, and for many, many years the righteous Christians would burn you alive if you dared suggest that the Earth was anything other than flat. I mean, seriously, you'd be burned alive if you suggested that the Earth was anything other than flat. And it's all a matter of perception based on how big you are. In 1 nanosecond, light goes barely 1 foot, 29.9 roughly centimeters. That's how fast light goes in a billionth of a second. So I got to shut up. I don't know if I got the idea of folded space across, going from the E equals mc squared to, I like to think of atoms as being Hoberman spheres, with the electron pairs being the joint. But even the Earth, Professor J.W. Gregory noticed that even the Earth is trying to take on a tetrahedral shape when viewed from the North Pole. So I'm going to shut up. That was my yak for today. I had to do something. So I'm going to say bye-bye for Butch, and thanks for watching.